Is we have already seen simple subnetting with the classful IP address arrangement, and today what we are going to see is variable length subnet masking with CIDR. So before starting this, let's see the whole story behind that. So as I told you that in classful IP addresses, there is class A where 8 bits are there in network part. Class B, we have 16 bit in the network part, and class C, we have 24 bits in the network part. So if we have class A IP address, we can connect roughly 2 to the power 24 hosts to that network. If we have class B network, we can connect 2 to the power 16 hosts to that network. And if we have class C, we can connect 2 to the power 8 hosts to that network. So let's stick to this particular these two. Just for example, suppose this is like 65,000 something, and this is 256. Now suppose I say that there is an organization which want to have a network, but its requirement is around 10,000 hosts. So what are the solution? What is the solution? Anybody? So if you get a class B network, you have 65,000 something hosts. If you have class C network, you can only have 256, around 256 minus 2 actually, minus 2 here also. But if there is an organization who require 10,000 hosts, what are the possible solutions? Anybody who want to answer?
One solution would be that multiple class C network connected with different networks. They are interconnected.
So what somebody is suggesting that inside that organization, I can have 50, around 50. If you multiply it by 50, we'll get around 10,000. Yes or no?
Yes, sir.
So you can have 50 class C networks inside, and then you can assign the hosts. This is one solution. But with this, what's the problem? That your organization will be identified not as a single network. Your organization would be, and to reach to your organization, routers before your organization have to maintain 50 entries. So it's true that you can, because if you take one class B IP address, there would be a lot of wastage. But if you take 50 class C IP addresses, IP class C networks, the wastage would not be there. But another issue is that all the routers which are behind you, your organization is reachable through series of routers. They have to maintain 50 entries for your organization, which is again is not a scalable idea. Are you getting the point, everybody? Yes or no? किसने आंसर किया था अभी? दिव्यांश ने आंसर किया था?
Yes, sir. Divyang.
Hmm. So is this okay if I say that if you have 50 networks, yeah, Divyansh, you have to maintain 50 different entries and all those routers uh, through which your organization is reachable. Anybody else want to say something? Yeah, Abhiraj. Hmm.
Yes, sir. Same answer means
Hmm.
if we use class C, then it will be cost effective, but many number of entries to means we have to maintain the 50 different
So
entries, and if we use
what is the possible solution?
to means we can keep at the starting only we can check
Hmm.
means at the starting the router has to check for all the 50 different
So
sub
so
networks.
so so the answer is actually that you need to remove these classes and make the whole arrangement classless. So how you can decide how many hosts a certain network can have? You just keep less number of bits in the host part. So when you say class A, we know that 8 bit in the network part. When we say class B, we say 16 bit in the network part. When we say class C, we say 24 bits in the network part out of 32, obviously. But when we say classless, then we need to have means to tell that how many bits are there in the network part. And that generally is known as slash notation. If I'm writing slash 18, it means 18 bits are in the network part, rest bits are host bit. If I'm writing slash 20, it means 20 bits in the network part and rest are host bits. So this was a paradigm shift from class full to classless. And now related to this is what we have seen up till now was fixed length subnet masking. We have seen the routing process where the subnet mask for all the networks were fixed. So when we have classless means through a router, different networks can get connected with variable sizes. And this router is going to have different size of subnets, different subnets for different network. The example, the case study we have seen in our class, previous class, that 4 networks and all are of same size. So actually every network was having same subnet mask. Fine. But now, because networks can have different sizes, we need to again do a paradigm shift from full length fixed length subnet masking to variable length subnet masking. So today's focus is VLSM and uh, CIDR classless interdomain routing. That's what we are going to see today in detail. So let's take one topology and suppose this is the topology. This is a whole big network of any company uh, who is operating. So let me take a snip. Fine. So this is a network, company network, who is operating in 4 offices. One is in Kuala Lumpur, other is in Perth, then Sydney, and then Singapore. And these routers are connected to the respective LANs of respective networks of these company offices. And you can see the LAN requirement of different offices, 60 hosts, 12 host, 12 host, and 28 hosts. And then these routers are interconnected also. Fine. Now, when we have a router, you might see this in our Cisco Packet Tracer laboratory experiments. In a router, which is actually a router, not a layer 3 switch, which is having a WAN interface also. So the WAN interface is wide area network interface through which this router is connected to another router. These are known as serial interfaces. And these links are known as point-to-point link. We'll see this later. On point-to-point link, which are connected through serial interfaces, Ethernet does not run. Ethernet is for shared media within a LAN. So these are dedicated link through which two routers are connected via serial interfaces of router. Here, point-to-point data link layer operates, and popular protocols are PPP and HDLC. We'll see PPP and HDLC in detail later. So these are layer 2 protocols which are running between point-to-point links. And these links are not shared links as in Ethernet. So you can see that for whole network 192.168.10.0/24, this particular address is assigned. It is /24 means 24 bits are in the network part. So safely we can say it's an old class C network. And now our goal is to assign IP addresses to different hosts which are connected in the LAN of these different offices. And as you can see, the requirement: Perth 60, Kuala Lumpur 28, Sydney 12, and Singapore 12. Now, I'm giving you 2 minutes to think. In this figure, how many subnets are there? How many subnets? Number of subnets. Can you just see and tell how many subnets are there?
Sir, 7.
Okay. How 7?
So one at the host and one at the other host, like for say Perth. Then again one at the host, and then one at Sydney. Then same one at Singapore, one at host again.
So you are saying this is one subnet. That's what you are saying. This is one subnet. Okay. 1, 2, 3, 4. Okay. Then
No, sir. One at the Perth end, one at the Sydney end, one at the Singapore end. Then the those three connections again at the
so you are saying
Kuala Lumpur.
these are also subnets. Okay.
Yes, sir. Yes.
So where are the hosts in these three subnets?
So at the two ends of the connection.
So this is one host and this is another host. That's what you are saying?
Yes.
Who are you? What's your name?
Sir, Tanmay.
Okay, Tanmay. So Tanmay is actually right, because router is also a computer, fine. And router also need to talk, and router also need to transfer packet from one router to another router. So when we are talking about serial links, so these two routers are acting as hosts to transfer data from one router to another router. And we'll see these things in detail later on. So safely these two can be considered as host, and because interface is changing and here the router is also changing, this is another subnet. So in total there are 7 subnets. Now if I follow our old process of subnetting to have 7 subnets, suppose I write this IP address 192.168.10.0/24, means there are 8 bits in the host part. And if you want to create 7 subnets, what you need to do? You need to take 3 bits out of this, and maybe from with old technology 4 bits. So if you take 3 bits, suppose, out of the host part, remaining are 4, 5, and maximum amount of host we can then connect is 32 minus 2 equal to 30. So if we follow the old process of creating subnets where every subnet is of equal size, then the maximum number of hosts where which every subnet can accommodate is 30. But our actual requirement is what? Our actual requirement, maximum requirement is 60. So we need to actually change the process of subnetting. We need to actually change the process of subnetting. And that's what we are going to learn in this class today. And then how, if the subnets are like this, how a data packet can be routed from one machine to another machine. Any questions anybody want to ask? Anybody want to ask anything? Okay, so the process is again purely mechanized. So you need to follow step by step and be very attentive. So the first rule is go for the maximum requirement first. So the maximum requirement is 60. So let's write down the IP address 192.168.10. Because it was /24, 8 bits were there in the host part. So for 60, we require how many bits in the host part? For 60, how many bits in the host part?
6 bits.
So if you take 6 bits, remaining 2 bits are this, so means you will extend the network by 2 bits. So if you write these 2 bits, the combination would be 0000011011. This is going to be the combination. So means what we are doing, if this is the address space of 0 to 255, we are dividing this address space into 4 equal parts. This is the first step when you want to assign 60 hosts. Here you are not required to exempt 00 and 11 combination. When not required, you can use 00 and 11 combination also. Because here I'll tell you that how it will not affect. So suppose if we take the first combination 00, so our 192.168.10.00 in the network part, which is extended, and now another 5 bits can move from all 0 to all 1. So what would be our subnet ID? Subnet ID would be this: 192.168.10.0. What was our overall network ID? 192.168.10.0. Again the confusion, but there is no confusion here because it was /24 and it is slash what?
26.
26. So now as soon as you attach the subnet mask or the number of bits which are in the network part, these are two different network addresses. So as soon as you say /26, you will see, okay, 26 bits, rest are 0, it is a subnet ID. So first subnet ID would be this. What is the broadcast ID? This would be the broadcast ID. What is this number? 192.168.10.63?
Yes, sir.
63. And from .1 to .62 can be valid host ID. .1 will be provided to the router interface, which is connected to the LAN. I mean to say this interface. The first usable host ID of this LAN, let me take the snip, means the first usable ID will be assigned to this interface. This interface. So let me write. So this is the subnet ID of this subnet is 192.168.10.0/26. Broadcast ID 192.168.10.63 slash. Don't forget to write slash. Otherwise, you'll not be able to see that what is the host part and whether all the host bit are 1. So from .1 to .62 are valid host ID. .1 will be assigned to this interface. So this interface would be having IP address 192.168.10.1/26. Similarly, the next biggest requirement is what? 28 host. The next requirement is 28 host. Now again, just see the process. So this was 0 to 255, the whole address space. We have utilized the first completely, means 192.168.10.00 is done. Next combination is 01. Now to get 28, how many bits are needed?
5.
5 bits. So 01. Now 1 bit is remaining. It can move in two manner, 0 and 1, and rest 5 bits can move from all 5 zeros to all 5 ones. So now what actually we are doing, we are picking up the second partition. We have partitioned into 4 parts. Now we are picking the second partition. First partition is assigned to Perth LAN, second partition, and we are again partitioning in it to 2 parts. See here, we are extending it by network part by 1 bit because 5 bits are required in the host. So let's take this combination. So our first subnet ID, because you are subnetting and then again subnetting it. It would be 192.168.10.01, then 0, and then all 0 to all ones. So what is this number? Obviously it would be what? 64, no? Yes or no? Slash?
Yes, sir.
Slash?
27.
27. And what is this number? This is 192.168.10.
64 plus
95 slash 27. Yes or no? Okay. Okay to everybody? Say yes or no. Anybody?
Yes, sir.
Okay. And now from dot 65 to dot 94 will be the host IDs, and dot 65 will be assigned to the interface. See here? Here the second subnet is 192.168.10.64/27. Broadcast address is 95/27, and the interface IP is 192.168.10.65. Okay. Now what are the next? Sorry, this is this. Sorry, 28. This whole thing is for this LAN. Got the point? Now what are the next requirements? Next requirement is 12 host. So what is required to be done? Now do it by yourself. So you can see this is assigned and this is also assigned. What is remaining? This is remaining. So now we'll take the next combination. So 192.168.10.00, then 0 we have taken, sorry, 01, 01 we have taken, we have extended it by 1 bit, that 1 bit 0 is taken, now next is 1, this bit. For 12 host, how many bits?
4.
4 bits. So 4 bits means 1 bit is again here, 0 and 1. So if you see, actually we are again dividing this particular thing into 2 equal parts. So 60, 64 rather, then 32, then 16 and 16. Okay. So if you take the first combination, it is 192.168.10.0110, all 0 and all 1. What is this number?
96.
96. So our subnet ID would be 192.168.10.96 slash
28.
28. Broadcast ID would be what?
1111.
Broadcast ID 111
Yes,
slash
sir.
28, and the usable IP address is at .97.2.110, and .97 will be assigned to the router interface. Now, Perth is done. Sorry, what is the figure? Sorry. Perth is done, Kuala Lumpur is done, Singapore is done. Now Sydney. Sydney again 12 host. So what we'll do? We'll use this combination. Okay? And you know that what you'll get, the next subnet will be .112/28, and it will go up to 127/28. .113 would be the router interface, and something like that. Now all these four, and we can see in the slides also one by one. So this is the first subnet, as you can see, network address, 63 broadcast address, .1 is given to router interface. Fine. If you go to the next, 64/27 is a network address, 95/27 is a broadcast address, and router interface is assigned with .65. If you go next, .96 to .111 is a broadcast address, but here it is /28. Fine. And the first 97 is assigned to the router interface. If you go further, 112 to 127 and 113 will be assigned to the router interface. Now, what about these subnets? How many hosts are there? In these three wire subnets, how many hosts are there?
Two.
Two hosts. How many bits are needed in the host part?
Two.
2 bits. Why?
Yes. Two we need to remaining for the broadcast and
obviously you require 2 bits, because if you take 1 bit, it will be 0 and 1. One will be network ID, other will be broadcast ID. So require 2 bits, 00, 01, 10, 11. So 00 will be the host ID, network ID, 11 will be the broadcast ID, and these two will be assigned to the interfaces. So things are very easy. Start from 112, which was the last one. Fine. And keep on assigning. And what you need to do, actually, just think about this particular figure. So it was like 16 to 8. So how many addresses are here if you see? So there were 64, 32, 16, 8, 8, and then 4. So you assign this, this, and this. Okay. And after you assign these 3 subnets, what is remaining? Even after assigning everything, this much would be left, which can be assigned later. So this, you can see, if you do in this manner variable length subnet matching, you are doing it very miserly. You are not wasting the IP addresses. So we were having 7 subnets. So 1, bigger one, then 2, then 3, then 4, 5, 6, and 7. So let me show you the IP addresses of these subnets. You can easily do them. One, so each WAN link requires 2 IP addresses. As you already told, that 2 bits are needed. 6 bits for extended network prefix of /30, because network bit will be of 30. And then if you apply here on 112/30, so you'll get this 128/30 network address, 131/30 broadcast address, and these two interfaces will be assigned. Second WAN link between Kuala Lumpur and Sydney, you continue from this 132/30 and 134/35/30, so on and so forth. So just applying the same process, you can get the IP addresses of wire interfaces also. Anybody is having any confusion? If any slightest of the confusion, you can ask questions. Divyansh, any doubts?
No, sir.
Aman Singh, any doubts? Okay, if there are no doubts, then we can move ahead. Now, let me show you the complete picture. This is the complete picture. So this is your LAN, the router interface, and then the wired interfaces, their IP address, everything is given here. And that's what I was showing you, that the whole 0 to 255 is divided like this. First quarter, then half of that quarter, then half to half of that quarter, and then /30/30/30. If you continue further, now what is needed is we need to write down the routing tables for this router. If anybody is sleeping, please wake up. The rules are very simple. If you want to configure the routing table for the Perth router, from Perth router, Divyansh, can you tell me how many networks are reachable?
Two networks.
I'm not saying directly reachable. So from Perth, if you want to go to the LAN of Sydney, you can go via Kuala Lumpur and Sydney router. Okay. So Perth to Kuala Lumpur to Sydney to the LAN of Sydney. If you want to go to this node somewhere in Singapore LAN, you can go to Perth to Kuala Lumpur to Singapore to LAN of the Singapore node. So what is the rule here? Please be with me. Take a router and a network and see how many networks are reachable from that router. How many networks are reachable from that router? List down all those network IDs. So as you can see from Perth, we have one LAN network 1, this wired network 2, LAN network of Sydney 3, LAN network of Singapore 4, wired network between Singapore and Kuala Lumpur, wired network between 5, then 6, and then 7. So from Perth router, 7 different networks are reachable. Maybe not directly, but via different routers. So the rule for constructing a routing tables is simple. Take up a router and first of all, list all the destinations which are reachable. So obviously, from Perth, we can reach 10.0, 10.136, 10.64, 10.132, all the subnets which are reachable. And then write the corresponding subnet mask. You can write in form of slash notation or in form of 255.255 dotted notation. So as you can see that this is the wired network /30 which is reachable, wired network /30 reachable, wired network /30 reachable, and then /26/27/28/28, all these networks are reachable. Now the important point here is, bacha log please be with me. Important point here is which networks are directly connected and which network you need to reach through another networks. That is the important point. The networks which are directly connected and networks for which you need to go through another network or another router. That is the important point which is mentioned here in this slide. Next hop. What is the next hop? This field was not there in our previous example because there was only one router. So you need to see about the next hop. Here you can see that 10.0 and 10.136. Let me see. Sorry. 10.0, this network, and 10.136, this wired network are directly connected. So what we'll write there, this is a generic routing table. Different devices, different operating system may write routing table in a different manner. We'll come back to that. This is a generic routing table that you write the destinations which are reachable. Second point, you write the subnet mask in second field for each destination. And third field, you write whether they are directly connected or you need to go through via some another router. So in Cisco devices, they write via. Yes? Any question?
ऊपर आते हुए सेरेलैक ले आओगे?
Please mute. So this is important here. So now we can see that this wire network .136, 10.0 are directly connected. So we'll write direct. Now if you want to go to 10.64, let's see the figure. Sorry. 10.64 is this network. So you are not required to know where this 10.64 is. You are just required that to reach 10.64, which next hop I should throw the packet. Which next hop I should throw the packet. So if you want to reach this LAN from Perth, obviously you need to go through Kuala Lumpur. Means you need to somehow throw this packet to this interface. Let me show you the snip of this particular slide and then it will be clear. What I'm saying that suppose from Perth you want to reach to any node here. So you don't worry where this network is. You just have to see that, okay, somehow I have to throw this packet out to the next hop. And which is my next hop? Which is my next hop in current network? My next hop is Kuala Lumpur router. And what is the IP address which is connected to this is this. So when I want to throw packet from Perth to this LAN, I need to throw the packet to the next hop whose IP address is given this. And that's what we have written in the next hop field, if you can see. That's what we have written in the next hop field. 10.138. 10.138 next hop. And to reach to this next hop, the final entry is important. So when we saying 10.0, it is directly connected. To reach to this network, which interface of router should I switch the packet? So you can write the name of the interface, serial के लिए S0, S1, Ethernet के लिए Eth1, Eth2. In this figure, I have written the IP addresses. So if you want to go to 10.0, it is directly connected, but which interface you should throw the packet out? That is, you can see the figure, that if you want to go from Perth to here in this LAN, it is directly connected, but you should throw the packet out of this interface. That's what is written as interface there, 10.1. If you want to go to 64, the next hop is this, but through which interface you should throw the packet out of this router is 1.137. You can see here. So if you want to go to 1.64, the next hop is this IP, but through which interface you should throw the packet out? This is the interface. All these points are important. 137. All these points are important. So there are 4 fields. One is network destination, second is subnet mask, third is next hop, and fourth is interface. There are other fields also in other implementations, operating system and devices, which I'll be discussing later when we see the routing process in detail. Now if I say that, suppose there is another router here which is connected to Kuala Lumpur. Now from Perth to Kuala Lumpur LAN, how many paths are there? Divyansh?
So 2 paths.
I can go either in this way,
or
yes, or I can go this to this to this. Yes.
Yes, sir.
Now here comes that now the question is, which is the next hop? You tell me.
It can be both, but the best would be the Kuala Lumpur one.
You can never say that because you are thinking right now it's 1 hop, it is 2 hop. Might be this is very busy at that time.
So can be both.
So that's what is the routing process. I told you, find the best path at that particular moment. So this routing process continuously keep on running. And depending upon whether right now best path is via Kuala Lumpur or via this X1, that is the result of this routing process. What is the routing process? We'll discuss. And depending upon the result of the routing process, the next hop and the interface entries will be decided. Is this clear to everybody?
So we don't manually fill in the routing table.
No, you don't do this.
Okay.
You just decide about the some entries you do it manually. Fine. Until unless, because the example I have taken right now just to make you people understand about the things is very simple, where these type of examples are known as stub networks, where there is only one way to go to the another network. Got the point, bacha? But,
yes, sir.
But if the topology is like that, then you can think about other things also. Okay? And then the routing process, because if you see the network is just a graph like thing. Okay? So router connected together. Fine. If you see the internet as a whole, as a complete picture, this will be set of routers. Now, if you want to go to LAN, this LAN to this LAN, there are many paths. No. So this router need to talk to each other that which is the best path. And that's why I say that routes are changing. Suppose you are transferring a 5 GB file, which may be converted into say 10,000 packets. So these 10,000 packets during the course of time may take different routes depending upon what is the best path at that time. So your simple Dijkstra's algorithm runs. Are you getting the point? We'll be coming to those points. Okay. Yes. Any questions? Any doubts? Any questions? If there are no question, then draw the routing table for Kuala Lumpur seeing this figure. Routing table for Kuala Lumpur router seeing this figure. 3 minutes. And you can raise your hand or you can interrupt me by your voice and you can show your output. 3 minutes. Start working. I can call anybody to open the camera and show the output.